Hello, everyone. This is actually my first time in Iceland, so I'm happy to be here. I'll be happy also to get off Iceland when the time comes. When Borje and Per asked me to do this, I was very, very thrilled. I mean, wow, an opportunity to talk in front of you guys. 2 seconds later, I said, what did I do to myself? I have to find some topic that I should challenge you with, and you guys will find interesting. And it's easy for me to dive into technical details, but I thought that would not be appropriate. So I picked this topic, which I think requires us to step back, and sometimes it requires us to step far back. So I will be talking about stuff that is philosophical, and I'm sure I'll get some reactions from you people. So I'm just putting the warning up front. I will try not to talk technical stuff. I think it's important when we design networks, design protocols, when we even just think about problems, that A, we attack the right problems, and B, we use the right approach. And only then we go to C and try to actually solve it, and D, try to evolve it, and so on. And as an engineer, I sometimes get stuck trying to solve the problem without even truly understanding the background. So I'm going to talk about centralized and distributed, and in the context of control planes. And I think one of the things that came out of this for me was control planes cover a large number of functions, a large number of different things that they do. And so we have to talk about centralized and distributed, but we also have to do it in the context of each of these functions. And in the course of doing this, I also needed some examples to test some theories. And so I took a few examples which are fairly artificial perhaps, but look at them not as proposals that I want to give you, but as a place to take something you understand and look at it a different way. Finally, I think because it is required to talk about clouds today, you saw it in René's talk, so I'm going to throw clouds in, whether it fits or not, just put it in there. And then I don't have conclusions. I'm going to leave you with a bunch of questions. And I think maybe in this audience, that's actually a good thing to do. But anyway, I don't have answers. I'm trying to make it good. So let's start with the internet. The internet is a very, very distributed system. And it's, of course, geographically distributed. There are lots of boxes, devices interconnected in various ways. And then if you look at the control plane that we use, the control plane is also very distributed. But if you look at the underlying things, for example, the transport network that goes under the routers and switches we connect together, they generally tend to be very centrally managed. So you have an NMS or some system that pokes each box and says, this is what you do, this is what you do, but all the intelligence lives up there. And recently, there's been some other trends that say we should go to that kind of approach. Our control plane should be centralized. So about 4 or 5 years ago, there was this thing called provider backbone transport, which essentially said we can do traffic engineering in Ethernet networks, but the way to do that is to have a centralized control of the traffic flows. So that's one way. And today we have another effort that says, again, something similar. You can have all your network boxes, treat them as dumb boxes, have an intelligent control plane which is centralized, and do what you need to do in your network. So René talked about innovation. Jeannie talks about innovation. For me, innovation says, let's play. Let's put our ideas that we might have had for a while aside and just think openly. Should the internet or any network system, routing, switching, data center, whatever network system that you think of, how should it be controlled? How should there be centralized intelligence, or should there be intelligence on each box working together? So here's a picture of a distributed control plane. You have a bunch of boxes that talk things to each other, typically ASes or BGP and BGP. Each box does operations on its own. So each box runs spanning tree. I should shoot myself now. Sorry. We'll get to the point where I shoot myself slightly later. So each box has to run shortest path algorithms, Dijkstra, and do BGP, and then figure out what the next hop should be, and then actually populate the routing tables. Now, you hope that when people are done, when these boxes are done, you have consistent routing. You don't always have consistent routing, but in a very short time, it should stabilize. But some people say, why hope? Why not just do it right? So what you have is instead treat all these boxes as fairly dumb boxes, put a magic box in the sky that has all the intelligence, all the state of the network, everything, and let it do all the computation, and then download to each of these boxes exactly what it should do. So the dumb boxes are only required to follow orders, and now you have a very nice network that does exactly what it's supposed to do. Looks good, right? So how do you implement this control plane, this centralized control plane, this magic box? You could have a single thread of control, a single process running on a single processor doing this. We know that this doesn't scale. So you could have a few processes with some inter-process communication doing this. So you have now a set of cooperating threads that say, we need to implement this control plane. Okay, so that's nice, but you need to actually run them somewhere. So ideally, you run them on a CPU. If you can get a CPU with multiple cores, you say, let me run it on that. Those cores have a bus between them, and that bus is a way for things to communicate. So maybe you're beginning to see the picture here. If one CPU wasn't enough, you take a few CPUs and put a little network between them. And now you say, I'm going to have lots of threads running on lots of CPUs, on lots of cores, on lots of CPUs, and they're all going to interact. What have I done? My control plane, my centralized control plane, is actually a distributed environment of its own. It's the only way we know how to scale. And you can call it centralized, you can call it distributed. If it makes you happy, go for it. But we have gone from a natural distributed environment where we had a network, we had physical separation, and we pulled it to another environment, which you might call an artificial distributed environment, with its own little mini network. The network between the CPUs, the buses within the CPUs, the inter-process communication. Have we actually improved anything? What fundamentally has changed? How did we end up here, and why? So I'll still call them centralized and distributed because that's convenient names. But essentially, if you look at these and try to compare them, one of the differences between a centralized and a distributed aspect, essentially what you've done is to take the intelligence from the box and put it somewhere else. Well, if you put it somewhere else and create this artificial network, you can partition the functions that you want to have happen in a different way than when you put them actually on the box. So in centralized control plane, you can say, I'll do topology discovery in this module. I'll do I did that again. Shortest path computation in this module. I'll signal the paths here. And so the result of all of this, of course, is my traffic patterns. But I've functionally composed it differently than maybe on a distributed system, which is every device has to do all the functions. So maybe that's a little bit better in the case of this, what we might call centralized approach. If you look at the standards, though, you have standards between the magic box in the sky and all the boxes down here. You don't have standards inside the magic box in the sky. Whereas if you have a device-based partitioning, you have standards between boxes all the time. So if I run ISIS and you run ISIS, we know exactly what we're talking. Yes, I do shortest path inside my box, and that's not standardized. I can do it any way I want, but most of the functions are between boxes, and all of those are standardized. The next few things I want to take off in a little more detail. But of course, there's one other thing that people come back and ask about, cost. Isn't it cheaper if you take the intelligence out of the box and centralize it and so on? So I'm not going to talk about that right now, but we'll come back to it. So the first thing is I can have intelligence on the box or in this magic box in the sky. Things happen. The network is constantly changing. And so the question is, how can we react? How do we know how to react? And how fast can we do that? So bad events like, there's a link failure or something, you can try to anticipate this happening and pre-program alternate paths and say, it's a dumb box, but not totally dumb. I'll give it 2 things to do, and if the primary doesn't work, it'll go after the secondary. There is a little bit of intelligence needed to figure out that something's wrong, and then everything's been pre-programmed. But for good events, this is a little harder, because you don't know what good event might happen. Again, you can try to anticipate a few, but it's a little bit harder to get there. The other thing there, though, is you might say it's okay to respond slowly to a good event. If a link fails, you're dropping traffic, you want to quickly go over to something else. For a good event, you might have a better path, but if you take a little while getting there, it's okay. But there are other events that are even harder to predict. And in this case, it may be the case that slow reaction is okay and may not be. So if you have a flash crowd or a distributed denial of service attack or a security breach, it's hard to anticipate, but it's not something you want to sit around for a while trying to figure out what to do. But one key thing here is effective reaction. So how do I know what the right thing to do is? And so the people who say, let's do centralized control plane, say that if I put all the information in one place and I put lots of CPU and lots of memory, I can really crunch out good answers. And yeah, this could be true. But I do want to go to a comparison of 2 protocols in the next slide, not because I like one or the other, but I just want to show you 2 different approaches to the protocols. But let me just take a simple example. Instead of having TCP work the way we do it today, why don't we send all the windowing information, all the ACKs and NACKs and everything to this magic box in the sky and say, please tell me what to do, instead of putting the intelligence in the box. I mean, think for yourself whether this approach might actually be better than what we're doing today. But I think that, again, we're trying to solve specific problems. If you step back, the network moves around a lot. Renee talked about mobility. Mobility is such a pain. It is. It's so convenient, but when you try to implement it. So you have mobility. You have flash crowds. You have so many things going on that by the point you've crunched out an optimal solution for something, that something is no longer valid. There are people who say we should do all this signaling to understand what is the congestion state in the network, and by the time you figure out what it isn't anymore. So for those of you like me, I would like to say with long beards, but you know the expression. If you remember, there was this attempt to have centralized economies that would take all the economic factors of a country or a system of countries and give you this perfect answer. They failed. Okay, so I'm just going to talk about PCE for a second. Nothing great. It means path computation element, and it's a protocol that essentially says, I've got really dumb boxes, they don't know how to compute paths, so I'll help them by this magic box in the sky. So the philosophy here is, I have to spoon feed these boxes in the network with exactly what they need. I mean, they can't think for themselves. So I will create this protocol where they can gather up everything they need, send it to this all-knowing oracle, and they'll come back and say, this is how you should signal the path. So there's a protocol. It's happily running along in the IETF. There's a new protocol that's sort of still being developed. And this protocol says something very different. It's truly not a box in the network. It's usually an application running somewhere else. But let's leave that part out. Essentially, it says there's an app in the network that needs information. I don't know how it wants to use the information. I don't know what it wants to do, but I'll act as a broker. It can come to me and say, here's the information I need, here's the characteristics, here's the types, and it'll come back and say, here are the values. And then that app has to go off and do what it needs to do. Optimize paths, redo the caches, whatever it does. In the first case, you said, here are dumb boxes, I'll spoon feed you, I'll hold your hands and do everything for you. Here you say, what you need is information, I'll give you that information. These are very different approaches. Before you even decide whether you want to do one or the other, you have to ask yourself, do I want intelligence in the network or intelligence over the network? Let's move on to managing, because the control plane does more than just steer traffic across the network. You want to talk about, how do I look at the boxes? How do I know what's going on? How do I troubleshoot? Here's a case where I think centralizing makes absolute sense. But I think it's really more about humans and their capability of dealing with many things, more than laws of physics or laws of networks. So the question I ask myself is, I have a network of 100 boxes. Do I want to SSH to all the 100 boxes to figure out what is going on, or SSH to some common place and say, tell me what happened or what is happening in the network? Also, it's easier to draw pretty pictures if you have a global view. So I think for this aspect of the control plane, centralization makes sense. One more thing is control of control planes, what some people call programmable networking or software-defined networking. I think this, especially for a research environment, this is really important. This is really key. The problem is, we've backed into this. We invented a protocol, we looked at that protocol and said, oh, by the way, let me do this. So now we'll talk about software-defined networking. I think we need to say, oh, software-defined networking is a huge idea. Let's figure out how to do that correctly. And if you step back and think of it that way, we write protocols so that they are syntactically extendable. And even that took a while because RIP, you have no ability to extend RIP. I know because I wrote the code for RIP for Juniper, and I had 16 bits I could play with, which is the tag. And that's the only bit of flexibility. OSPF, there's some extensibility, mostly in opaque LSAs. I'm kind of biased towards ASes. It's all TLV based, you know how to extend it. But having said all that, you don't have semantic extendability. I mean, you have, but you don't have a way of thinking about it. You know, if I take this particular TLV and add a new sub-TLV to it, syntactically it'll look like this. Or if I take this LSP and add such and such to it, this is what it'll look like. But what will the effect on the network be if I add this new function? So we don't have a semantic model to reason about network behavior. And because of that, we don't have a semantic model to reason about what happens if I insert this new way of doing things or change some way of doing things in an existing protocol. So what we have today is really programmed networks, not programmable networks. And I think we really need to get there. And it's part of René's innovation, so he's going to make you do it anyway, so might as well get started. We do have on-the-box SDKs, software development kits. I think it's a small step in the right direction, but it's a long way from saying we have a controllable control plane. So the question is it easier to build a controllable control plane when all of the control plane is in the centralized magic box in the sky, or when it's distributed? I think that's a wrong question. I mean, I don't know the answer, so I'm just not going to answer it, but I don't think that's the right question. I think you have to ask, how do I want to run my network? If I want to run my network in a distributed fashion, I have to figure out how to do a controllable control plane when the control plane is distributed. There's no point doing a centralized control plane, making it very programmable, saying, yes, that's what we want. Oh, now it's centralized. but I want to run a distributed network. Oh. Plan for success. If you do the experiment and you like the results, it should be something you can use. So if what you want is a distributed network, then, a distributed control plane, then find a way to have that kind of experiments. So I'm going to do these couple of experiments, or a couple of thought experiments, that I'm not recommending one or the other, but just so you can think about things. So you have your familiar BGP network. You've got eBGP sessions on the outside, iBGP sessions on the inside. Each of these boxes essentially gets the eBGP sessions, looks at the routes, gets iBGP route updates, does best path selection, does whatever it does, and installs information into the FIB, into the forwarding trees. Furthermore, it might say, based on all this information, I'm not only going to install forwarding information, I'm also going to install unicast RPF information so I can block traffic that comes from sources that I don't expect. So this is what we do. What if I said, these boxes are dumb and they're not working fast enough and they can't have enough of whatever they need to have, or they're too expensive? What if I said, I'll pretend that my BGP session terminates, I don't know if this works. I'm not even going to try. I'm just going to pretend that my BGP session terminates on this box, but actually tunnel the packets up to this centralized BGP server. And so this box is sort of just gathering all the information, sending it up, and then all the other BGP boxes do the same. So you have this huge number of sessions coming into the centralized BGP, which we will, of course, implement in a distributed fashion so it scales. So what do you do up there? You're essentially doing the union of all the work that you were doing in these nodes down in the network itself. Now, having done that, you churn through all your policies and all your path selection and everything. You come up with the route table for each of these boxes. Now you have to download them back to the box. And if in addition you're doing unicast RPF, then you have to compute those as well and download them to the box. I don't think you've fundamentally reduced work. You might have increased work. But you did this in the centralized fashion, so that might be nice. Might be nice. So there's another thing that you did, though, which may not be as obvious. In the network, you have this thing called iBGP. It's a standardized protocol that boxes interact with each other. When you tunnel all the packets into the centralized BGP, iBGP goes away. How that box interacts within itself, how it produces routes, how it does route oscillation, whatever it does, that's inside the box, and the door is closed. So could I have a multi-vendor implementation of this magic box in the sky? I can have multi-vendor implementations of the blue boxes at the bottom in the network. But this magic box in the sky, is it standardized? Is it standards-based? The north-south protocol by which that box talks over these tunnels to all the boxes in the network, you can standardize that. But the box itself, all the heavy lifting done inside, it's a closed situation. I'll take one other example, fighting DDoS, and this is a familiar example. I just want to illustrate something. Let's say that there's some distributed attack on that server hanging off in the middle. Now, what happens is it's hard to detect individual attacks on the server coming in from the edges. But when you get to that central point where the attack occurs, the signature is much easier to find. So what you want to do is to detect DDoS attacks centrally, especially at the point of attack. But then when you want to implement your filters to stop it or reduce it, you need to implement the filters on the edge. So you have a situation here where essentially you want to make decisions centrally and you want to do implementation in a distributed fashion. This is typically how policies happen. And the reason I'm saying this is You can talk about the control plane as being an entity that steers packets, and you can ask, is that centralized or should that be centralized or distributed? You can talk about management, and there it's, for me, fairly clear it should be centralized. You can talk about BGP, and should that be centralized or distributed? For DDoS, it's not a clear, it should be centralized or it should be distributed. There are aspects that should be centralized, there are aspects that should be distributed. Finally, clouds. It's mandatory. What is a cloud? I have actually no idea what a cloud is, but I'm going to make up something. Single centralized mega data center where magic happens. Except if I put everything in one place and that place, something happens, I lose everything. So I need to geographically distribute it so that I can have redundancy. I can follow the moon, which is a really bad expression, meaning I can use electricity in the time zones that makes most sense. But, things are so far away, and I have problems with latency, I have problems with bandwidth utilization and so on. So I'm going to put caches in my network, and so that people are happier. So then I need an infrastructure for doing all this. Okay, if you want to call this centralized, I'm happy for you. But for me, a cloud is a complex, geographically distributed entity that is shown to the user of the cloud as a simple, centralized entity. You're telling the customer, you just access the cloud, and magic, the right things will happen. Your traffic will go where it needs to go, your data will get back to you, everything will happen. The fact that it has a very complex, distributed implementation is hidden from you. So here you have a situation where it's not that some parts are implemented centrally and some parts are implemented in a distributed fashion. Essentially, because human beings like things to look centralized, you make them look centralized, but you implement them the way it makes sense for you. So this thing about central and distributed is really, it has to fit the problem, and it has to also fit the human capability for knowledge. And maybe I'm just projecting my deficiencies on the rest of you. If you guys are okay with managing 500 boxes, sorry, this is just me. So how did we get here? I don't know. Somebody else is driving. But I will take a lesson, and I keep saying spanning tree. Now I'll actually say spanning tree. I'll take a lesson from way back when. They were building Ethernet networks. They wanted to put redundancy in it. The moment they did that, they had loops. They said, oh, what do I do about this? And they were given a few choices. One of the choices was run ASes, run a link state protocol. They said, we don't have enough memory. We don't have enough CPU. This would cost too much, blah, 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 blah. So based on that excuse, they said, we will run this other protocol called spanning tree. Very much less work to do, much less compute, very much less memory that you need, and very much less stuff on the wire between boxes. So great. So they implemented the spanning tree. And then as computers got better, as the onboard chips got better, what they did was not to change from spanning tree to ASes, but to go from spanning tree to rapid spanning tree, and then to multiple spanning tree. But they stayed with spanning tree. They stayed with spanning tree, in my opinion, 25 years too long, and paid for it. Well, a lot of people paid for it. The thing is, you make a decision based on cost, based on the current state of technology, based on any of these things, and you don't say, this is a suboptimal decision, you're doomed. You're going to stick with it until it's taken out of your cold, dead fingers. I mean, you're just going to hold on to it way beyond it to be held. So all I will say here is, if you make decisions based on cost, based on the current, I can't put that Cray supercomputer in my router, and so I'm going to go to a completely centralized control plane. You will have to live with that decision for longer than you think. And especially as researchers, I think you should say, well, I mean, it's a cost-constrained environment for everyone, so everyone wants to be able to save a little money here and there. But as engineers, I think we are a little more constrained and perhaps should be somewhat constrained by the cost of something that we do. Whereas researchers, I think, should be able to say, there is a cost component here, but this is how we would recommend to do it. But, you know. So you guys all paid a lot of money to come here, but my advice is free. Don't underestimate the power of the on-box computer. Every year, it gets better and better. We can put more CPUs, more cores. Well, typically not more gigahertz anymore. That's because of other problems. But you get more cores, you get multiple CPUs, much more memory. All of this keeps improving. And if you say, I'm constrained by that today, wait a year, and it gets better. It'll always be the case that compute outside of the box will be more powerful than compute in the box. By the box, I mean a router, a switch, TDM device, or whatever. However, if you go by that logic, you'll never get anything done. What you need to say is the compute in the box good enough? If not this year, next year. And what's the trajectory of that? More than that, you have not just one box, you have a distributed system. You have 100 boxes. If you get them working together the right way, you have a lot of compute there. So what you should be more concerned about is, what's the information exchange? What's the processing model? How do I get these boxes cooperate and do the thing that needs to be done, rather than push the work somewhere else? The interaction between boxes, I think, is something else. We've had a long time, we used to program in assembly language not that long ago, and then we were programming in C. But now we're trying to move up the ladder and program in object-oriented languages and interpreted languages and so on. We're doing the same with the boxes now. We're saying, here's a box, it wants to talk to that box. Let's talk at a really low level, as opposed to what's the right level of interaction between boxes so that we can get this work done efficiently. And behind that is, that box is really dumb. I have to spell everything out to it, versus stepping back and saying, I can give it a high-level command, and it can interpret it and operate on it. So the last thing is the one I mentioned earlier a little bit, which is it's easy to standardize what goes on between boxes. It's hard to standardize what's inside the box. And so if you now change your model of a control plane so that you put more and more inside the box, that's closed. And you could try to get in and try to break it up, but that's a hard thing to do. Oops. Okay, so in conclusion, I'm concluding without giving you conclusions. There are lots of things to think about. And actually, for me, this was a lot of fun. Because my day-to-day job makes me do all kinds of things that I may or may not want to do. But here it was just step back and think about things. And for me, a control plane used to be just the part of the box that steers packets, that gets routing to happen the right way. But there are a lot more aspects to control planes. And for each one, we need to figure out whether we should use, and for want of a better term, I'm still going to say distributed and centralized. Should these functions be on-box or off-box, essentially? And when you decide that, you should also keep at the back of your mind, what's the information distribution model that I can get these functions working the right way? And take the PCE and Alto example as two methodologies of information distribution. Is the box I'm dealing with really dumb and I want to spoon feed things? Or is the box that I'm dealing with reasonably intelligent but doesn't have certain bits of information and wants to go to an information broker, round out its information and then process on its own? And then once you get there, you have to also ask, how do we structure protocols so that this kind of interaction is doable? So that I give that box the information that it needs and let it do its own processing. The second part is about programmable networking, which is what is the semantic equivalent of extensibility? how do I make a protocol semantically extensible? When I write protocols, how can I start thinking about that early so that I won't write a protocol and find that it's a fixed dead-end protocol? What's the semantic model by which we can reason about device interactions so that I can then use that to understand what a hot insertion of a new semantic model would mean to the network or to a particular service. And then lastly, just coming back to management, I think, I don't have an answer for this, but I think we do management in a very poor way. And the right interaction between computers doing a lot of thinking, I shouldn't call it thinking, processing and crunching of numbers, and humans interacting with them to get the right information. I don't think we've structured this right, and I don't think we're doing the right thing. But the net result of this is, I don't know in research networks, but in commercial networks, OPEX, operational expenses, is typically 2/3 to 4/5 the cost of the entire network. And that's just a ridiculous number. We have so much potential help, and we can't get that right. So anyway, that's all I had.
Thank you. We have time for questions.
This one there.
Currently, one of MPLS-TP objectives is to make it possible to work with MPLS-TP box with a zero control plane.
With the zero?
Yeah, without. Oh, zero control plane.
Zero control plane.
Yeah,
yes,
make it
yes,
possible.
Yes.
In your opinion, is it a false objective or not?
How much trouble do you want me to get into? First of all, if you define control plane loosely enough, it's not really about zero control plane. It's really about zero control plane on the box, because you're moving it from the box to the magic box in the sky. So essentially what MPLS-TP, which is why the subtitle of the talk is, do you want the internet to run on static routing? Essentially, the magic box in the sky will do all the work for you and then install static routes on all the boxes, which is one way of doing things. MPLS-TP says you can run a dynamic control plane on the boxes, or you can run a control plane in the sky. So from that point of view, yes, that is one of the objectives. But it comes from the transport people who think that boxes are dumb and will never get smart, and so we need to do all the work in a network management systems. So if you look at any other, ATM is a great example. We have this very well-defined protocol, PNNI, for routing and signaling, but essentially all ATM networks are centrally provisioned by an NMS system. It's the transport mentality. I shouldn't say that. I get in trouble all the time.
Thank you.
Over here? Yes. Oh, Max, sorry.
Just shout.
Somebody got in front of you, but next.
Yeah.
Can you
I'll repeat it. Yeah.
Wait.
So is this what the Iceland students do for fun? They come to the university cinema to hear Nordnet speeches.
Thank you for an insightful talk. My question is, so I think it's fine, centralized, distributed. It's still, someone came up with the algorithm, has coded it, whether they coded it in a distributed manner or a centralized manner.
Yeah.
It displays uniform behavior. The question is that you have left the user and the application. So in either case, you consider the application and the user dumb. Give me the packet, I'll take care of it. I know what's best you want. The thing what gets people going, or why people go these different directions, which may not be ideal in a true architectural sense, is because they want a level of control, and everyone wants a different level of control, which is where the programmability comes.
Yes.
That's what people are trying to really solve, not debate between centralized and distributed. And the way they solve it is to get centralized brokers of that desire or need, and then they implement it in a distributed manner.
So I agree with you. And I think we're saying the same thing. What I'm trying to say is we've sort of backed ourselves and discovered the need for programmability. If we set that ourselves up, that's the goal, then whether we need a centralized approach or even centralized brokers or whatever it is comes second. What we have now is these different approaches and then saying, oh, can we make this programmable? So that's why I say step back, and sometimes you have to step back 2 or 3 steps. Do we have the right infrastructure for a programmable, a controllable network? And if we do, then go ahead. If we don't, how can we change it? So I think we're saying the same thing. And you're right too that ultimately, I'm a networking geek, so I'm only worried about the network piece. But then you can step back and say, do we have the right things for the applications to do what they need? And Alto is trying to extend, do that to some extent. We've had, even before Aon, which was a Cisco buzzword for application-oriented networks and so on. So at some level, you have to get back and say, are we giving applications the freedom they need to use the network the way they need to? Then, users.
The RNA networking community has its own sets of things or widgets it's creating. So we go to at least make sure that you're in sync with those as well.
Which committee is this?
The RNE.
RNE, yeah. Okay, yes. Okay, so the comment was the RNE networking committee is on the way there, so good. There was a question down here. Oh, okay.
Further questions? In that case, let's thank the speaker again.